Yesterday, I drew a picture of a model of the atom on the board for us, and we had two things inside the middle of this model of the atom, and then we had one thing orbiting around that middle thing. What's in that middle thing, in that nucleus? Yeah, good. We got the protons and the neutrons in that middle thing. The protons are positively charged and relative to the rest of the atom at least, relatively heavy. The neutrons are neutral and are also relatively heavy relative to the rest of the atom, that is. The neutrons, we're probably not going to talk about for the rest of the unit. They're neutral. They, for the most part, don't matter when we're talking about electrical interactions. Later on this year, when we talk about nuclear physics, the neutrons become pretty important. But right now, they're not really very important. The protons, we're not going to look at very often either, although they are charged, positively charged. It's mostly the negatively charged electrons that are orbiting around the nucleus that we care about in this unit. Why is that the case? Why is it the electrons that we care more about than the protons? Yep, Chase? Good. If something's going to move around from one to the other, one material to another, it's going to be the electrons. Chase, why is it that it's easier for the electrons to move around from one to the other than it is for the protons? Good. They're not as tightly bound to the nucleus. They don't require as much energy to leave the atom as the protons do. The protons are held in place inside the nucleus by this really strong force that we call the strong nuclear force. And that's a big force, and it doesn't want to be overcome. It can be. Okay, when we talk about nuclear physics in our last unit, we'll learn that that strong nuclear force can be beaten. It can be overcome, but not by rubbing a balloon against your hair and then sticking it against the wall. When you do that, you're only going to overcome that electric force that keeps the electron in orbit around. So if something's going to move, it's going to be the electron. It's the movement of electrons that produces electricity. That's really what we care about for the most part in this unit. Now, we learned about charge yesterday as well, and where negative and positive charge comes from. We learned that a positively charged object comes from having not just protons, but rather having more protons than electrons. Good. And a negatively charged object comes from having more electrons than protons. What is the charge of an electron, by the way? The symbol for charge is a Q. What is the charge of an electron? Anybody remember that from yesterday? You don't need to remember it, by the way, right? Remember I told you don't need to memorize that number, although by the end of the unit, you'll probably have it memorized. Yeah, Logan? The unit is the coulomb. Yeah, the unit is the coulomb. And a coulomb, remember, is a pretty big unit of charge, right? It takes a lot of electrons to make up a full coulomb of charge. Matt, do you remember what the actual charge is in coulombs? Or do you remember where to find it, one of the two? Good. Negative 1.60 times 10 to the minus 19 coulombs. So Matt remembered that number. Some of you are going to remember that number right now. Some of you will never remember it. That's okay. Look on your data sheet if you don't remember it, right? Where do you find it on your data sheet? Well, if you go over to the right-hand side, it says the charge of an electron is negative 1 E. What does that mean? What does that E mean? We showed you this yesterday, right, August? Yeah, it's the elementary charge. And the elementary charge has a value of 1.60 times 10 to the minus 19. That's on the left-hand side of our data sheet. So look on the right-hand side, negative 1E. Then look on the left-hand side to remember what an E is. It tells you on the left-hand side that an E is 1.60 times 10 to the minus 19 coulombs. So using those two things, you can determine the charge of an electron is negative 1.6 times 10 to the minus 19 coulombs. A proton, by the way, is positive 1.6 times 10 to the minus 19. It's positive 1E. Yesterday, we also calculated a number of electrons. You guys remember the analogy that I gave you yesterday with the oranges? One orange was 200 grams. We had a total mass in the bag of oranges of 600 grams. How many oranges were there? You guys all knew the answer was 3, right? We did that by finding the total mass and dividing it by the mass of one orange. In that case, it was 600 grams divided by 200 grams gave me 3 oranges. What am I going to do if I want to find the number of electrons? Emma? Good. It's the total charge divided by the charge of one electron, which is, of course, 1.60 times 10 to the minus 19 coulombs. If you want to find a number of anything in physics 30, and there are going to be other things later on that we have to find a number of anything. One of the things in our fourth unit that we have to find is a number of photons. You don't even know what a photon is right now, but you will then. Okay? It's the total of something divided by the amount for one. Okay, for the number of photons, it will be the total energy actually divided by the energy for one. But just remember that you got to have a total amount of something and then an amount for one of something and then divide the two, and that's going to give you the number of whatever it is that you're looking for. Is that okay? You guys remember the difference between a conductor and an insulator? Yeah, the electrons are free to move, not the protons, right? We already established that it's going to be the electrons that move. Okay, a conductor is something that allows the electricity to flow because the electrons aren't as tightly bound to the nucleus in a conductor. Can you give me the general category of materials that tend to be the best conductors? Metals, yeah. And insulators, that's the other one. Insulators are materials that their outermost electrons aren't as free to move. They're more tightly bound to the nucleus. Doesn't mean that they can't move. The insulators will allow electrons to flow. If you stand outside in the rain, okay, with a aluminum baseball bat sticking up in the air, okay, you might get struck by lightning, even if you have rubber-soled shoes on. And rubber's a good insulator. It's a really good insulator. But that rubber can still conduct electricity from your body to the ground. Okay, it doesn't mean just because it's an insulator that it doesn't conduct, it just doesn't conduct nearly as well as it does if you had metal-soled shoes or something, or steel-toed boots or something like that. Okay, still conducts electricity, just not nearly as well. And the general category of materials there would be non-metals, things like plastic and wood and glass and so on. Yep. Well, yeah, you know what? I'll be honest with you. If you get struck by lightning and you're wondering which shoes you should be wearing, it probably doesn't matter. It probably doesn't matter. Theoretically, I suppose, to a very, very tiny degree, the rubber-soled shoes would be better, but it's not going to make much of a difference. If lightning can go from the cloud to the ground, from the cloud to you, then it's easily going to go through the rubber that's this thick into the ground, right? Even though rubber's a good insulator. So I suppose that it would conduct slightly better, well, a lot better, I guess, through steel-toed shoes, boots than it would through rubber-soled shoes, but you're still going to get way more than enough going through the rubber-soled shoes to kill you, basically. The three laws of the electric charge, who remembers what one of those is? Doesn't matter what order we give them in. Remember Newton's laws we talked about in Physics 20? There was the first law, there was the second law, there was the third law, and it mattered what order we had those in, right? Newton's first law was always an object in motion stays in motion and so on. It doesn't matter what order we give these in. It's not like the first law and the second law and the third law. We just need to know all three laws. Matt, what's one of them? Yeah, opposite charges attract. Okay, so if we've got a positive and a negative, they're going to attract each other. Good. What's another one of the three laws? Whatever the order you want to give them to me. Chase? Good. Like charges repel. That means that positive repels positive, negative repels negative. Repel, by the way, means they push each other apart. Positive pushes apart, positive, negative pushes apart, negative. Finally, what's the last one? Yep, Matt. Good. Charged objects attract neutral objects. What did I say yesterday was one of the really important words in this sentence that we didn't really explain yesterday that we'd come to explain today? Objects. Good. Charged objects attract neutral objects. And you're going to learn in about 20 minutes why charged objects attract neutral objects. For now, just trust me that they do. Good. All right, I'm going to give you one more law that you didn't do yesterday now that's not really with these three. It's kind of a separate thing. It's called the law of conservation of charge. You guys will remember from physics 20, the law of conservation of energy. Energy can't be created or destroyed. The law of conservation of matter, you would have learned in chemistry or even Science 9 or Science 10. Matter can't be created or destroyed. The law of conservation of momentum, we went through in most of the last unit. It essentially said, we phrased it a little bit differently, but it boiled down to momentum can't be created or destroyed. So the law of conservation of blank would say blank can't be created or destroyed. The law of conservation of charge would say specifically that charge can't be created or destroyed. We can transfer it from one thing to another. When you rub the balloon against your hair, the balloon becomes negative, your hair becomes positive. You've transferred charge from your hair to the balloon, but you haven't created it and you haven't destroyed it.
Good morning, everybody. I apologize for the interruption.
There are a number of places this year where we will use the law of conservation of charge. One of those times is just dealing with a simple interaction between two objects that are charged. When we touch two objects together, we transfer charge from one to the other, but we don't create or destroy. So we're going to use the law of conservation of charge to describe that transfer that's taking place. What charges want to do, the natural tendency, is to reach a point of equilibrium. If we have an object that is roughly the same size, roughly the same shape, roughly the same material as another object, and they touch together, then the charges will balance. So if one of them was neutral and one of them was -5, then they'll balance out to be -2.5 and -2.5. Or if one of them was 5 and one of them was 7, then they'll balance out to be 6 and 6. Now, that doesn't always happen. If one object happens to be pointy and the other is rounded, okay, the one that's rounded will hold more charge. If one happens to be really, really big and one's really, really small, then the one that's really big will hold more charge. Okay, but in the end, if the materials are roughly equal size, equal shape, equal materials, and so on, then they're going to balance out. And that's what we want to look at in question example number 2 here that you got yesterday on the handout. Here we've got our two objects, similar size, similar shape, similar material. They momentarily touch each other. So they touch each other and then they're separated again. The first object had a charge of 2 times 10 to the minus 6 coulombs, which, by the way, we could also write as 2.00 microcoulombs. Okay, 2 microcoulombs. Well, the second object initially had a charge of -3 times 10 to the minus 6, or we could say it's -3 microcoulombs. Determine the final charge on both objects, which objects gained electrons, which objects lost electrons. Let's deal with the final charge first here. Assuming the natural tendency takes place, and that is to balance out the charges, all we have to do is take an average of these two charges to figure out what the charge on each object is going to be after the interaction. So we're going to say 2 times 10 to the negative 6 coulombs plus -3 times 10 to the negative 6 coulombs is going to give me, divided by 2 is going to give me a value of what? Well, 2 plus 3 is -1. -1 divided by 2 is 0.5. Get 5.0 times 10 to the negative 7 coulombs. So one of them was 2, one of them was -3. Now after they touch each other, they both become 5 times 10 to the minus 7. Right, what was the total charge before they touched? -1. Sorry, this should be -0.5, right? -0.5 times 10 to the minus 7. What was the total charge before they touched? -1 times 10 to the minus 6. What's the total charge after they touch? Well, if we add this up, -5 plus -5, we get -1 times 10 to the minus 6 coulombs. Total charge remained the same, right? Just got redistributed. The law of conservation of charge says the total charge has to remain the same, although we can redistribute it. Which object gained electrons? Well, we had one that was positive, it became negative. We had one that was negative, it became a little less negative. Which one gained electrons? If one of them was positive and it became negative, then it must have gained electrons. So this is the one that gained electrons. And if this one was negative and it became less negative, right, 3 times 10 to the minus 6, 5 times 10 to the minus 7, it became less negative, then that must have lost electrons. Here's another one. Example number 3, this is the bottom of the page that I handed out yesterday. It says ball number 1 initially has a charge of 3 coulombs. That's a lot of charge, right? 3 coulombs, but whatever. Ball number 1 touches ball number 2, which initially has a charge of negative 1 coulombs. Ball number 1 and 2 are separated. And then ball number 1 touches ball number 3, which has a charge of negative 5 coulombs. So let me get this straight. This is kind of confusing, right? Ball number 1 touches number 2, and then they separate. And then ball number 1 touches number 3. What do the charges on all 3 of them become? How do I deal with this? Take all 3 charges, add them up, divide by 3? No, can we? No, I see you going like this. No? You know it's not that, though. Okay? You're right, it's not. So how am I going to deal with it? All right, Joshua?
First find the charge of ball 2.
Okay, so let's deal with 1 and 2. 1 and 2 are touching each other. Then let's deal with 1 and 3 separately from that. Let's create a little table to help us with this, okay? Here's 1, 2, and 3. Initially, those charges are plus 3, minus 1, and minus 5. The total charge there, by the way, look, the total charge is what? Minus 6 plus 3 is minus 3. That's the total. Number 1 touches number 2. 3 plus negative 1 is 2. Divided by 2 is 1. So they become plus 1 and plus 1. Right, what do you think your common mistake would be here? And if this was a multiple choice question, the options would reflect that common mistake. Yeah?
Ended there.
Well, yeah, it could be ending there.
Or you could just apply, go ahead and apply the negative 3 to the 2 and 3.
The more common mistake is actually to leave it at 2, right? We add these up. 3 plus negative 1 is 2. To write in 2 and 2. Okay, which can't be right. We had 3 and negative 1 gives me plus 2. Well, we can't all of a sudden just make charge and now have plus 4. It still has to be plus 2. We're going to divide that up, though, as plus 1 and plus 1. Now, number 3 stays as minus 5 because nothing's happened to it yet. It hasn't been touched anything yet. But now we're going to touch number 1 and number 3 together. Plus 1. Oh, by the way, let's add these up just to make sure that we're still good here. 1 and negative 5 gives me neg 3. The total charge is still neg 3. Now 1 touches neg 5. 1 plus negative 5 is neg 4. Divided by 2 is neg 2 and neg 2. Number 2 stays the same because it's not involved in this one. Let's add these up. Neg 2 plus 1, neg 2 gives me neg 3. Total charge is still neg 3. Looks like it works for us here. All right? If these 3 objects touched each other at the same time, as opposed to one touching another, then separated, and then so on and so on and so on, what would we do? Here's add them up, divide by 3. That's an easier question. We just don't see that very often. Okay, usually it's one thing touches one more, and then successive things can happen there. But, all right. Today I want to focus primarily on how we give objects charge. We talked about negative objects and positive objects and gaining electrons, negative electrons. But how does that happen? Like, what's the mechanism by which objects become charged? Well, there are two general categories of charging objects. One is called charging by conduction. Conduction always involves a transfer of charge. Always. And induction never involves a charge transfer. I'm going to put a little star by that because there is kind of a little asterisk that I got to point out later on, but we're going to say that it never involves a charge transfer. So if you're walking up to somebody on the carpet and you stick out your finger and you touch their finger and you shock them, electrons have been transferred from you to them, that must have been charging by conduction because it was a transfer of charge taking place. Conduction usually involves touching. Although not always, it usually involves touching. If I walk up to somebody and I touch them and I transfer electrons from me to them, then that's conduction. But sometimes what can happen is I can walk up to somebody on the carpet, build up so much charge on myself, I touch their finger or I go to touch their finger, but the electrons actually jump or arc before we make contact. That's still charging by conduction, even though they're not actually touching. It's like they're touching. They almost touched. There's a transfer of charge taking place, so it's still going to be conduction. Induction never involves touching. Now we've got a couple subcategories of conduction. Subcategories that the Alberta Physics 30 diploma exam people don't always differentiate between the two. Sometimes they just consider it all one big category. We'll differentiate between the two just in case. Charging by friction is a type of conduction, and that basically involves rubbing things together. It's the rubbing conduction. If I rub a piece of plastic against a piece of dead rabbit or rabbit fur, then there'll be some charging going on. You can hear it actually discharging. Can you hear that? One of them will become positive, one of them will become negative. If they were both neutral and the plastic became -10, then by the law of conservation of charge, the rabbit fur would have to become +10, right? Total charge has to remain the same. See it a little bit there? See the hair going up a little bit there? Okay, so this had to have become charged, right? Because it was causing a force of attraction with the hair. Okay, charging by friction. Now, charging by contact would occur by touching or by getting close enough to be like touching. So if I walk across the carpet and I go to touch Joshua's finger and I shock him just before we touch, that counts, even though it's not touching. It's close to touching. Charging by contact, which sometimes we just call conduction, even though it's actually a subcategory of that. Okay, those are the easy ones. Now we get charging by induction, which doesn't involve a charge transfer. We get two subcategories for that, and these are a little bit more important. All right, let's make the induction category a little bit bigger so we have some more space. I want to draw a couple of pictures here to illustrate what's going on when we charge objects by induction. First of all, we're going to have an object here that is neutrally charged. We're drawing 3 positives, 3 negatives. It doesn't really matter how many we draw as long as there's an equal number of positives and negatives so that it indicates that it's neutral. Nearby that, I want to bring a negatively charged object. Now, of course, that's not just containing electrons. There's protons in there as well, but we're just showing it as containing electrons because we want to show you that it's going to be negatively charged. Doesn't matter where we put it, left to the left, to the right. Doesn't matter whether it's rectangular or square or circular, whatever. Okay, it's irrelevant. It's negatively charged. When I bring that negatively charged object nearby the neutral object, tell me what's going to happen to the protons in this neutral object. Be careful, because there's a bit of a trick here.
They're gonna draw in the electrons, and the electrons will draw in the protons.
Yeah, that's what they want to do. They want to be attracted to the electrons in this thing, right? Because they're oppositely charged. But the protons can't go anywhere, right? Remember, the protons are stuck in that nucleus, so they can't go anywhere.
It's mainly the electrons are being drawn towards.
Yeah. Yeah, absolutely. These electrons would be drawn towards the left-hand side. But more importantly here, bless you, more importantly here, these electrons in this neutral object are pushed away by these electrons over here. So what we're going to get is not necessarily all of them, but a number of the electrons on the right-hand side are going to be pushed as far away from the negatively charged charging object as possible. Now, the charge on this ball is still neutral, because it's still 3 positives and 3 negatives. But now what we've got is a separation of charge. One side is negative, and one side is positive. Overall neutral, but the charge is separated. Now, why do we add that word temporary in the front there? Why is it a temporary separation of charge? What's going to happen? What's going to happen if I take away this negatively charged object? Yeah? Yeah, they're going to more or less rebalance out, right? The separation is going to be gone. Let's draw another one now. This is still under temporary separation of charge. This time, we've got a neutral object, but we've also got a positively charged object. Again, still some electrons there, but more protons than electrons. What's going to happen to the protons in the neutral object? Oh, it's not as much of a trick as it was the last time. Protons aren't going to go anywhere. They can't. They're too tightly bound in the nucleus. What's going to happen to these electrons? Yeah, these electrons get drawn towards this positively charged charging object. So once again, we still have a neutral object, but we have a separation of charge so that this side is positive and this side is negative. Now, remember that third law of electric charge? I said charged objects attract neutral objects. This is why. This is neutral overall. But the side of this neutral object that's closest to the charging object is positive. It's opposite to the charging object. And opposites attract. So why do charged objects attract neutral objects? Well, really, it comes down to they attract neutral objects because positive attracts negative. We have an induced separation of charge, which causes the closest side to be opposite. Look over here. The closest side is negative. The object is positive. Opposites attract. All right? Notice charges weren't being transferred there, right? Okay, notice they weren't touching. Yeah, go ahead, Shiva. How does it charge it? Well, it doesn't really make it negatively charged or positively charged. It just creates a temporary separation of charge. So it makes one side negative and one side positive. So it's a little bit different charging. But we can make it permanent. We can make this thing positively charged by induction, permanently by induction. And we're going to do that by introducing what we call a ground wire. You guys ever heard of grounding? Or what a ground wire is? Huh? Yeah. Yeah, it's a path for electrons to either flow into the ground, literally into the ground, or out of the ground. Depends on the scenario here. You have ground wires in your house. Okay, the idea there is if you have a short circuit in your house, then these extra electrons flow into the ground as opposed to cause your house to to burn down. And that ground wire in your house, you could find it easily. If you go down to your basement, there's going to be a copper wire, a thick copper wire that goes into your electrical box downstairs. It's probably going to be uncovered, okay, and you'll be able to see it right away. You follow it, and you'll find that it actually goes out the wall of your basement, and then it'll go down the side of your house, literally into the ground, 6 or 8 feet into the ground, and it stops. That's it. It stops right in the ground. And the idea is, again, extra electrons can go into the ground and drain there as opposed to generating this heat and causing a fire in your house. So what's going to go on here? Well, these green electrons are pushed as far away from the negatively charged object as we can go. Now they can go even further. Now these green electrons can keep going down into the ground. Now what are we left with here? This isn't neutral anymore with a positive side and a negative side. This is positive now, right? Because the electrons are gone, or at least some of them are gone. We've now just charged this positive by induction. But it's not permanent yet. Because if we take this away, it's just going to go back to the way it was. The electrons will come back up from the ground and then redistribute. So here's what we got to do. Remove the ground wire or cut the ground wire. Now the electrons want to go back up where they were, but they can't because they don't have a path. Some of you might look at this and say, well, like electrons are being transferred into the ground. Isn't that conduction? Well, yeah, it actually is. Conduction is taking place from the object to the ground. But the overall process is still called induction because the thing that's doing the charging isn't touching and isn't transferring. So we still call it induction, even though there's a little bit of conduction taking place within that. All right, what happens over here? Well, here we got a positive object that is going to attract electrons up from the ground. Now we got a bunch of electrons, extra electrons in there. It makes it negatively charged. If we cut the ground wire, it remains negatively charged. So Shiva, you were asking a few minutes, how is that really charging? Well, when we charge something by induction, creating a temporary separation of charge, it's kind of charging, it's kind of not, because the overall object is still neutral, but it's got a separation. Now it's actually charged, right? Now it's actually positive or negatively charged. Here's an example of an application that applies what we've been learning for the last little while here today. This is called an electrostatic precipitator. If you go down to your basement, to your furnace room, you're going to find on the side of your furnace a slot where you can pull in and out this furnace filter. And you're supposed to change those things every 3 months. The idea is that it mechanically takes dust and pollutants out of the air as the air is forced through the furnace and then up through your furnace vents. Now, it's a mechanical system. That means if the particles are too small, they'll go right through that filter. This is a different kind of filter that does essentially the same thing. This is an electrostatic filter. So this can suck out really, really tiny particles of dust or of pollutants. There's a fan down here somewhere that's blowing air, like raw air, like dust-filled air, through this electrostatic precipitator. These green dots here, these green circles, represent dust particles or other pollutants that are neutral. Okay, they're right from just whatever appears in the air. You know how sometimes the sunlight comes in through the living room and you see all this dust in the air? It's like, holy cow, we're breathing that all the time? Okay. That's what we're talking about. It's this dust-filled air that's being blown through this electrostatic precipitator. Now, you got these blue rods that are negatively charged. Now, I'm not sure in the photocopy that you have if you can see that they're negatively charged or not, but they are. They're negatively charged because they're attached to the negative side of the power supply here, versus these red plates that are positively charged because they're attached to the positive side of the power supply. Now, this air that contains these neutral dust particles are going through these negatively charged rods, and they're touching them. And as they do, we get some charging by conduction taking place. Electrons transfer from the blue rods to these green dust particles. That makes these dust particles negative. When negative touches neutral, they both become negative. So now these dust particles aren't neutral anymore, they're negative as electrons are transferred to them. Now these negatively charged dust particles go through these red positively charged plates. Now what's going to happen to them? They're going to get attracted. So these negatively charged dust particles get attracted to the positively charged plates, and then what goes out the other side? Clean air, because the negatively charged dust particles were attracted electrically to these positively charged plates. Okay, that's a much better way of dealing with the dust than a mechanical system because we're not dependent upon the size. Okay, we don't need to have big dust particles to get filtered out. That make sense? Yeah, go ahead.
I have a question. And that is, with the negatively charged dust particles become neutral and then going through?
When they touch this,
Yeah.
okay, the negatively charged dust particles, there's potential for them to lose some electrons in there. Sure, there's potential for that, but for the most part, they're going to stick to this. Okay, oppositely charged is going to stick to this. There can be some charge transfer, but because these dust particles aren't particularly good conductors, you're still going to maintain some of that negative charge on there most likely, and therefore it's going to stay, for the most part, stay there. Let's take a look at one more, and then we're done for the day here. So this is the house I'm going to buy, or the backyard that I'm going to buy when I win the lottery tomorrow. Okay, when I win 649 tomorrow, this is going to be mine. Now, it's a bit of fixer-upper, as you can see, my swimming pool in my backyard on the ocean with my wrought iron fence painted. Got to paint that fence. But I'm too lazy to go with a paintbrush and paint it. It's going to take too long to do that. So I want to use an air compressor and blow the paint at it, right? Spray the paint at it. But man, that could create a big mess, right? The nice concrete patio that I have around my pool is going to get paint on it. I might get paint in my pool. So what do? Well, I use an electrostatic painter. An electrostatic painter has a rod in it that's charged. It could be charged positive or negative. Doesn't really matter. We'll make it negative. Paint gets blown through this electrostatic painter. And as these neutral paint particles go past this negatively charged rod, what happens to them? They become charged negatively by conduction, because they're touching. So now we have these negatively charged paint particles rather than the neutral paint particles that we would normally have. These negatively charged paint particles become attracted to this metal fence that is grounded, right? It's grounded because it's literally into the ground. These negatively charged paint particles are attracted to it. So what's the benefit of this over just regular spraying paint? Yeah?
Basically, the paint's homing into, like, just...
Yeah, you know what? That's a good way to say it, actually. The paint is homing towards the metal rods here. If we look at this kind of on a different way from above, these paint particles, even if they weren't charged, would strike the object. But these paint particles would miss and create a big mess. But if this object attracts these paint particles because the paint particles are charged, then what do you end up getting? Yeah, they're homing towards it. Now, they're not all going to strike it, but you're going to get a lot more of the paint particles striking it. And that creates a couple of advantages, right? One, a lot less mess, right? A lot less mess. And two, a lot less wasted paint, right? A lot of times we paint cars like this. You paint cars like this because it provides better coverage, right? Better coverage around turns and through cracks and so on. But it also creates less mess, and it also uses less paint, which saves money. Okay, Logan, question? No? Yep. Could you create a positive charge on the fence? Well, I suppose you could somehow, but it's not necessary actually for this.
Because the charged object
Yeah, the charged object is attracted to the neutral object, and we ground that as well. The fence is easy to ground because it's just automatically grounded, right? If you're doing the car, painting the car, then you would ground the car as well. It's not necessary to give it a positive charge. Although, like say, if you did, then yeah, then it would be automatically attracted to it as well. I suppose if you made it positively charged, then you'd get some attraction even if the paint particles weren't charged, right? You get more if they were negatively charged, but get some even if they were neutral.